Now in this video we discuss about the examples. Consider a matrix A, and suppose you are provided with this matrix A and you want to find the projection matrix. First we need to check whether the columns are orthogonal to each other. If I denote this column with A1 and this column with A2, so A1 is 2, better not to add comma here, 2 1 3, and A2 is 0 1 1, and I compute A1 prime A2, then it is of course equal to 4, which is not 0. So these are not orthogonal to each other. And we then define B1 as we had in the previous videos, A2 A1 divided by A1 square length times, this is the coefficient, and this is A1. If I do the computation, then it is given by 4 divided by 14, 213, which I can simply write it as 2 divided by 7, 213. So you see we can find then B1, and simply B2 is A2 minus B1. If we do the same computation, we will get to this B2. Therefore, I can construct the projection matrix. But here, if we look at B1, B2, let's compute B1 transpose B2 to see whether these are orthogonal to each other. We will see it is minus 8 plus 5 plus 3, which is equal to 0. So I can conclude that B1 is orthogonal to B2. In this case, you can easily write the projection matrix based on the vectors B. Remember from the previous video. So I can write the projection matrix as the sum of BI transpose BI, inverse BI transpose, which here I varies from 1 to 2. Because B1 is orthogonal to B2. So if I follow this way, I can simply, after some algebra, get P equal to this matrix here on the right hand side. Another way is, okay, we can start with a matrix which has the orthogonal columns. A better choice for A would be A equal to these two columns, or matrix with this matrix 3 by 2 with these two columns. Since we can replace the first column with this transformation in the original matrix. So if I have this original matrix and I compute half A minus A1 minus A2, then I can find this A matrix here. The good thing is that this A matrix has orthogonal columns, so I can easily write B1 and B2 based on the these two orthogonal columns. And if we follow the same route and construct B1 and B2, once again we can construct the projection matrix with this formula. So if I use B1 and B2, I will get the same result as above. You see these two matrices are the same. Another way is to use the result of vector space orthogonal to V. Now I will come back to the notes. If I consider A again, here let's write A. This is the A matrix that we started. So this is the third way in order to find the projection matrix. V is actually generated by two independent columns. So according to the note that we already had in the previous video, the dimension of these two orthogonal spaces is equal to, sorry for this minus here, it's actually the orthogonal space to V is equal to the number of rows. So it is equal to 3 if you remember from the note. So here I can get the dimension of the orthogonal vector space as 3 minus 2, and here 2 comes from the dimension of V, which is the dimension of the two independent columns. It is equal to 1. So we can find one basis. We can find a basis vector in the orthogonal space, which I call it E, and E can be in V, such that AI prime E is equal to 0, which is because it is orthogonal. And that can give you a basis that we can, with this basis you can easily find the rest of the solution. With some try, we can find that, okay, this E can have this form. So after some computation, if you multiply, for instance, if you get A1 prime E, it is equal to 0. Also A2 prime E is equal to 0. So you see that this is the basis that we were seeking for that. And if you remember from the previous video, if I have the projection matrix P, I can also use I minus P, and this is the identity matrix. And in this case, the projection is given by this formula. This, remember, P is orthogonal to, or better say, this V perpendicular is orthogonal to V. In order to see that, if I have the projection in V and the projection in V perpendicular is I minus P, if I multiply both, then P minus P2, since P is idempotent, I can write it P minus P, which is equal to 0. It means that these two are orthogonal to each other. So I can use E in order to construct the elements of I minus P. But here we have E, so we can easily construct the projection matrix. And this we can consider as another way in order to find the projection matrix. So we can skip this example too. Suppose that you provided with this A matrix, and we stick for orthogonal basis for V. First of all, note that according to the previous note that we had, these two columns are independent. It means that the inner product is equal to 0. So I can write the dimension of V plus dimension of the orthogonal space as number of rows, which is equal to 3. So once again, I can get the dimension of the orthogonal space as 3 minus 2, which is equal to 1. So we have one basis vector, I call it E, and we must have AI prime E is equal to 0 for I equal to 1 and 2. In this way, we can construct the orthogonal matrix. So we follow with this B. An orthogonal basis for V is the columns of a matrix B, and simply with these columns I can construct a projection matrix. Once again, we can with a try we can find a basis E, which from similar to the previous result, we can find the projection matrix in the exactly in the same fashion as we discussed in the previous example. Now we get to sum of squares of linear sets, and this is actually the important part in order to see how we can use the response or expected values in conjunction with projection matrices. Suppose that y is an n by 1 vector with the expected value is equal to mu. So I assume that the expected value of y is equal to mu, and the variance, or better said, variance covariance matrix is equal to sigma square identity matrix. The sum of a square of linear functions, we consider linear function, and then we come back to this coefficient here. Here, when you say c prime y, it means that c1 y1 plus c2 y2. So I can write it as sum of ci yi from 1 to n. Okay? The sum of squares of linear functions is defined as the sum of a square of lengths of projection y onto c. And from the main theorem in the first video, we know that the projection of y onto c can be obtained by this formula. If you remember, it was a coefficient. This is the coefficient multiplied by the vector that you project on it. So this is actually the projection. And when I find the length of the square length, it means that I multiply by itself. So after simple linear algebra, you will get this formula. And it's pretty simple in order to see that. Remember that c prime y is scalar. So when you have a scalar, the transpose is equal to itself. So they are equal to each other. I can write it this way. Sorry. I can write it y prime c. So those are equal to each other. So I can say, I can take one of them and power 2. Then you will have c prime c. One of the c prime c in the denominator vanishes with simplifies with the 1 in the denominator, and then you will get this result. This actually sum of square, the same as the sum of square of linear functions d c prime y. Why d? Because if you consider the sum of square of a coefficient for any non-zero constant, it will be in the numerator and denominator, and it vanishes. So this will be the same. Then it follows, if I get an expected value from s square, if I define this as sum of square of linear function and I get the expected value, then simply the denominator is constant. So it's constant, and it comes out from the expected value, and you have the expected value of c prime 1 power 2. We know that if we are provided with a random variable, the variance of, let's say, y, or you may also say the variance covariance, not a problem, x the expected value y prime y plus minus expected value of y prime expected value of y. This is for the trace, and if you want to get a matrix, then the variance of y is actually expected value of y, expected value of y prime minus expected value of y. I must correct this one. Sorry. This is for the variance covariance matrix. So it is a matrix. This is the expected value of y prime. Remember here, this is a matrix minus expected value of y, expected value of y prime. Okay, in any way, since it's a scalar, we do not need such a computation here, and we can say the expected value of c prime y power 2 is equal to variance plus the expected value power 2. So we can easily get that. But the variance of this guy, the variance of c prime y is actually equal to C prime variance of y c. And from the assumption, this is the variance of y. So we can say it is sigma c prime c. And if you divide it by c prime c in the denominator, then you will get sigma square as the variance plus the expected value of c prime 1 power 2 divided by c prime c. So the expected value of s square is sigma square plus a term which is obtained by replacing the random variable by the expected values in s square. Therefore, we can conclude if the expected value of y is equal to 0, or in general the expected value of c prime y is equal to 0, then I can conclude that the expected value of the sum of square of linear functions is equal to sigma square. And if it is equal to sigma squared, then we can easily get the expected value of c prime y equal to 0. The sum of the squares of a linear set is defined similarly. Up to now, we define sum of the square of linear functions. Now we want to define a sum of the square of linear sets. Suppose that C is a matrix n by m, and you can construct it this way, and you can present it vector-wise, C1, C2 up to Cm. Each of them is of dimension n by 1, sorry. And assume that the rank of C is equal to R. Further, suppose VC, the vector space, it's a column space, is generated by the columns of C. And let's see LC, the linear set of all linear functions, is defined by this way. So I define the linear set as any linear function of y which the coefficient belongs to this vector space. Actually, we call LC the linear set which is constructed by C is generated by linear functions. The linear functions are dependent or independent corresponding to dependency or independency of the coefficients. Any R independent linear function in LC will therefore generate a linear set LC. We say that LC has R degrees of freedom. So if this is the case and you have R independent linear function in order to construct a set, then you said it is the degrees of freedom of the set. Now let's consider the sum of squares of the sets. The sum of square of linear set LC is defined as the square length of the projection of y on VC, like you define for the linear functions. You define as the projection of y on C. Now when we work with sets, we define the projection of y onto VC. And it can be then constructed this way. This is actually the projection on y. So we have this transpose in order to construct S square. And if I do a little bit algebra, then I will get to this expression: var prime C prime C generalized inverse. I do not put transpose because you know that the C prime C generalized inverse transpose is also a generalized inverse for C prime C. So we will keep this one. You're familiar with such a notation. Let me put T here. Then we have C transpose. Then I'll multiply the second term, generalized inverse C prime Y. Now, according to the definition of generalized inverse, I can write it as one generalized inverse. So we have C prime C generalized inverse C prime Y. And it comes from uniqueness as symmetrical and also idempotency. So we understand that. The expression for S squared is independent of the specific function Cy, which generated by LC. So it means that you can also take it to orthogonal space. What I mean by orthogonal space, if you remember from the previous video, we said in order to have a convenient and nice representation for projection matrix, we can construct a matrix based on the given original matrix, which the columns are orthogonal to each other. So I can define a B matrix based on the given C, and then I can write S squared based on the element of V. But when you write it based on the element of B, if you remember from the previous video, the columns are orthogonal to each other. So you can have a better representation for that. I keep Y prime. This whole term here, let me just use another color. This whole term, if you remember from the second video, it is actually this term here. I expanded, and then I will come back again to Y. So if I multiply it, I will get a very nice expression for that, which you can then compare with the previous result and see, okay, I can then write S squared, which is the better say square length of projection of Y on VC, as the sum of small si, which are actually projection, a square length of projection of Y on or better say this, projection of Y on C. And this is also at the same time sum square of B prime Y. So we could make a connection between the projection which obtains works on the set, and projection which work on the columns of matrix. And simply, if you get the expected value of a square, you can, based on the linear properties of expected value, you can write it the expected value of I square. Once again, I'll write it based on the variance of Si plus the expected value of Si power 2. So I can simply get this formula for that. If I represent it as S sub mu square, then we will see the expected value of S square, which is the square length of the projection of Y onto the space, is equal to R sigma square if and only if the expected value of B prime Y or this guy at the top is equal to 0. So instead you can write this equal to 0. But this happens if and only if the expected value of C prime Y is equal to 0. Because there is a relation between B and C, and you can then remember from the first video. So if it happens, then we can say the expected value of S square is equal to R sigma square. Now suppose VC1 and VC2 are two vector spaces generated by C1, the columns of C1 and columns of C2, each has respectively rank R1 and R2. But more importantly, mutually orthogonal vector spaces. When we say mutually orthogonal vector spaces, we can conclude that C1 prime C2 is equal to 0. Now construct the spaces, better say construct the space VC as the sum of these two, and the sets L as the sum of these two sets. The implication that we obtain is that VC is actually generated by the columns of C1 and C2. And if we represent SI2 as the sum square of LCI, which we just recently discussed, then I can write the sum of a square of the VC, better say LC, as the sum of these two sum of squares. So I can write S square as S1 square plus S2 square. With the same reasoning, we can come up to extension to K sets and k matrices. If I can write the vector space generated by the columns of C as the sum of vector spaces started by matrices C1, C2 up to Ck, and also the set of C as the sum of set of C1 plus C2 up to Ck, then I can write the sum of a square based on the sum of squares in the current corresponding linear sets. Now let's back to the final point and consider a set LC, which is started as the linear functions on y when the coefficients belongs to this vector space started by the columns of C, and also assume the rank of C is equal to R. The mean square for LC is equal to S squared divided by R. When we say the mean square, it means that you divide the sum of a square by the rank. And the expected value is simply, if you remember, the expected value of S square was equal to R sigma square plus expected value of B times Y. And if we divide it by R, we can simply get this expression. So you will see if if in general S square sub mu is equal to 0, then the mean is equal to sigma square. Now let's do a little bit of numerical computation here. Suppose that y is a vector of dimension 4 by 1, and mu is the mean of y is given by this vector. Also suppose C1 and C2 are these two matrices. You will first immediately understand that, okay, these two columns are orthogonal to each other, and these two columns are also orthogonal to each other. So I can easily conclude that C1 transpose C2 is also equal to 0. It means that also these two matrices are orthogonal to each other. Then we can say the sum of squares of linear sets LC1 and LC2 are actually based on the computation that we had above, or better say not this one, is equal to y prime C1, better say C1. So we can say for the first C y, and if for a moment I denote the columns with a small c, let's say it is small c1, this one is small c2. So from the above result, I can also write this as y prime small c1 transpose small c1 generalized inverse, here it must be capital C, small c1y plus y small c2 transpose small c2 generalized inverse small c2 y. And you can see if I take C1 as 1 1 0 0 and I multiply it with, or better say transpose and multiply with C1 and also multiply the elements of y. Let me write the elements of y here. Keep in mind that the elements of y are like something like y1, y2, y3 is a column vector. Then you can simply get this C1 transpose y power 2 divided by C1. These are actually small c. C2 transpose y power 2 and then C2. And if I consider C1 and C2 as these two columns and multiply with y, then I can easily get this result. It is equal to half y1 plus y2 power 2 plus half y3 plus y4 power 2. We can do the same thing for C2. So I can write S2 based on C2. The same formula. I'm not gonna repeat the whole, just write the general one. So, and if I name these columns as small c and do the same thing, we will get S2 square as by this formula. So the total sum of a square, if you remember, the total sum of a square is S1 square plus S2 square, which I can find it in this way. And if you get the expected value you can simply find it from the variance and the expected value, as we already discussed, and we will have the expected value for the sum of a square of for S. We can also have the same result for another example. Suppose y is n by 1. The expected value is mu. The variance covariance matrix is given by sigma square identity matrix. And we consider the set of all linear functions of y generated by IY. I here is identity matrix. So if I do proper multiplication with some algebra, S square is given by the sum of a square lengths of y. Also note that the linear functions y1 to yn form actually mutually orthogonal bases for this linear set. So the sum of a square S square is actually the same as the total of individual sum of squares of yi. And if I consider yi as a e or residual or remainder vector, which the ith element is equal to 1 and the rest is equal to 0, then si square is yi square, simply. So we can construct Le, the set of linear functions orthogonal to y bar, and this e is because of this vector here. The sum of square of Le is then y prime 1 minus n y bar power 2, and you see it is actually the remainder, or sum square of error you consider in linear modeling. And the mean square error, I can then divide it by the rank, which is n minus 1. So this is the sum, the mean square of L, the set, and the expected value can easily be obtained with this formula. Also, we can find this expected value. The result is pretty simple and straightforward, so I didn't want to repeat it again in order to make the video very short. Thank you for listening.